Ring ring, telephone, rank rank, maths video. We've already explained what is the rank of a matrix. It's the number of rows and columns left over when combos made up of other rows or columns are removed. Or, to put it in a slightly more complicated way, the rank of a matrix is the number of linearly independent row vectors and column vectors. So far, so good. But how do you calculate the rank when you've got an already completed matrix? Let's snatch a matrix from the wild. We'll have to tinker with this one. Logically, we don't want to change the rank in the process. There are only three things we can do with matrices if we want the rank to remain the same. You may swap rows or columns. You can also multiply rows or columns with numbers. And you can add rows or columns together or subtract them from one another. Therefore, you can also add multiples of a row or column to another, which is just a combination of the other things. Why are we tinkering with the matrix? We do not want to change the rank, but we want to change the matrix in such a way that the rank is immediately visible. For this, we want to transform the matrix in such a way that it contains as many rows and columns as possible that only have zeros. Once you've done that, you'll be left with just rows and columns that you can't transform doing that. There, you can do what you want, no zeros will be coming out of them. The number of those rows or columns will then indicate the rank. So first up, we'll transform our lines and columns so that there are as many zeros as possible. The first thing we're trying to do is to manage to get ones right across the diagonals of the matrix. Or in non-square matrices, there where the number of the row and of the column are the same. First row, first column. Second row, second column, and so on. And then we want to have only zeros left in the column. So that here must be 0. This one here, and this one. At the first row, first column position, we want to end up with a 1. It's already there. Nice! Now, as to the rest, we want zeros in the first column. In the second row, there's a 2. So, subtract the first row twice. We'll first mentally multiply the first row by 2, and then subtract the numbers from the corresponding numbers in the second row, which leaves us with this here. In the third row, we can see a 3 at the front. So, multiply the first row in your head by 3 and subtract it from the third row, which leaves us with this. Right, we now want there to be a 1 in the second row of the second column, but there's still a 0 there. From 0, you can never get 1, no matter what you multiply it by. But don't panic, we can swap columns and rows. How about the second and third columns, for example? Which leaves us with this here. Now the 1 is where it should be. Now, as before, we just have to get zeros in the columns. So, this here has to be 0. We take the middle row and subtract it twice from the top row, and again from the bottom row. Let's take a little break for you to work it out in peace. Press pause. This is the result. So, now we still want for there to be a 1 in the third row of the third column. That fits in again. Other than that, there should be only zeros in the third column. Almost fits, just the third row to subtract twice over from the first row, which leaves us with this here. So now we can't go any further with row transformations. There are no more 0 rows to be obtained. This means that there are 3 rows left. You can now add up the columns. Let's not write in such detail for the moment. The first column added 12 times to the fourth, the second and third each subtracted 3 times from the fourth. Then you come out with something like this. And we did all of that with the help of transformations. We have a 0 column and 3 columns or rows that do not equal 0. Logically, when it comes to rows and columns, we have to end up with the same result. The rank of the matrix, therefore, is 3. It is often but not always the case, by the way, that you'll find zeros right across the diagonals. Sometimes it is also the case that just a few entries on the diagonal are 0, no matter how many more times you continue to transform. But what do you do when there are zeros in the diagonals as well? Absolutely nothing at all. In this case, you just need to pay attention to the rest of the diagonal entries that are 1s. The rank here would again be 3 because the first, the second, and the fourth row and column do not contain only zeros. So, how do you calculate the rank of matrices? You can swap rows or columns, multiply with numbers, or add or subtract. The aim of the transformation is to get as many 0 rows and 0 columns as possible. The number of rows or columns that can't be made into null rows or columns thus equals the rank of the matrix. As an intermediate step, it is quite useful to make the entries on the diagonals into 1s and make the rest in the column zeros, just as we did with this matrix. Some diagonal entries can also be 0, but don't mind that. Take a look at our next videos to see all the other stuff you can do with matrices.